We're going to recap the main ideas from waves, which you've probably seen before at GCSE. So there's lots of different types of waves. We have surface water waves, which are different from waves crashing on a beach. Those are a bit more complex. You'll have heard of the electromagnetic spectrum. So lots of different categories of waves, visible light, X-rays, gamma rays, and so on. Earthquake waves as well, certain types of earthquake waves we will consider. And most waves, although not all waves, will need a medium to travel through. These are called mechanical waves. So water waves, earthquake waves, sound waves need some substance to travel through. However, light waves and all waves in the electromagnetic spectrum are not mechanical. They do not need a medium to travel through. Right, the two main categories of waves which you've probably come across before, transverse and longitudinal. So many waves are transverse waves, for example light waves, surface water waves, all the waves in the electromagnetic spectrum, and they're represented by this very wavy diagram as shown here. And the definition is the vibrations, or the particles, if it's a mechanical wave, vibrate in this direction, which is perpendicular 90 degrees to the direction of travel. So that's our definition of transverse waves. Longitudinal waves, also known as compression waves, sound waves will be an example of that, and certain types of earthquake waves. If we have this representation as shown here, then if it's particles in a sound wave, the vibrations are in the same direction, backwards and forwards. That's parallel to the direction of travel. So these are a lot harder to represent diagrammatically. So sometimes, and confusingly, transverse waves are used to represent a longitudinal wave. So watch out for that. Very often you might be shown a transverse wave, and that's fine to represent a sound wave, but sometimes the question will say, what type of wave is a sound wave? And it's a longitudinal wave. Right, so some of the key terms. So the wavelength is the distance from peak to peak, or even better, the distance between two identical points on adjacent waves. That's given the symbol lambda, which is this upside down y. The amplitude is the maximum displacement from the equilibrium position. So be careful, it's not the total displacement, it's only from the midpoint to either the peak or the midpoint to the trough. The time period, that's straightforward. That's the time taken for one complete oscillation. The frequency is the number of vibrations per unit time. And there's a simple relationship between T and F. They're inversely proportional. So T is equal to 1 over F, F is equal to 1 over T. We can make the distinction between pitch and frequency. They both mean similar things, but pitch is used for sound waves. This is a musical term, so a higher frequency relates to a higher pitch. But frequency is the better, more generic term. Most waves we'll look at are known as progressive waves, which means that energy travels from a point outwards, sometimes in all directions, maybe like a light wave, or along a particular path, like a water wave or a wave on a string. So most waves we'll consider are progressive waves. It's only later on in the topic, when we consider stationary waves, that those are slightly different, as we'll see. So just be careful with the representation of waves. So we would always have displacement on the y-axis. So this, for example, a transverse wave, this is the oscillation which is perpendicular to the direction of travel. In this case, we have distance represented on the x-axis. In this case, peak to peak, as shown, would be the wavelength, because that's the distance. Another way to represent a wave would be to have time on the x-axis. In this case, peak to peak is not the wavelength, but it's the time period. However, in both cases, if we have displacement on the y-axis, then this arrow shown here vertically, that's the displacement from the equilibrium position to the peak. That is the amplitude in both cases. So just be careful when you're representing waves or looking at a graph in an exam question. Always take note, what does the x-axis represent? This is the wave equation. You've probably seen this before. Now, you've probably used at GCSE the symbol V for velocity, which would make a lot more sense. Some exam boards use C, which can be a bit confusing because very often we use C to represent the speed of light, which it may well do if we're talking about electromagnetic waves. So C or V represents the speed or the velocity in meters per second. The frequency, as we know, is measured in hertz, and the wavelength is measured in meters. Now we can derive this formula, and we may look at that later on in this series. So we have a few worked examples. If you want to, you can pause the video and try these with your calculator, but I'm going to work through these now. So these are all pretty much GCSE level. So the first one, nice and easy, speed or velocity is equal to f times lambda, 15 times 4, 60 meters per second. Now if you think about it, this should make sense, because if I have a wave which is 4 meters long, and I have 15 of these per second, then the total distance in 1 second will be 15 times by 4, 60 meters per second, which is our speed. We can rearrange this to make f the subject. So f is equal to v or c divided by lambda. So that's going to be 340 divided by 20 in this case, 17 hertz, 17 waves per second. If we're referring to any waves in the EM spectrum, so light or gamma or microwaves, they travel at the speed of light, which is 3 times 10 to the 8. And we need to be quite confident with our prefixes, so killers in this case. So we need to make lambda the subject, lambda equals v over f. So we have 3 times 10 to the 8 divided by 15,000, and we get 20,000 meters, or 20 kilometers. So if we're talking about some waves, the wavelengths can be very, very large. If we're talking about radio waves, all the way down to absolutely tiny, if we're referring to gamma radiation, gamma waves. Then the final one, the frequency, f is equal to v over lambda. Sometimes they won't tell you the speed. They just expect you to know that the speed of EM waves is 3 times 10 to the 8, the speed of light. So that's our velocity in this case. 8.5 centimeters, we need meters, so divide by 100. And we get 3.5 times 10 to the 9. We do need to know the prefixes, so very often in the exam you'll be asked to write your answer in megahertz or gigahertz. So giga is 10 to the 9, so it's 3.5 gigahertz.